Yes, thank you for the introduction. And so, as you stated, this paper on the adaptive multi-antenna receiver has been co-authored by my colleague Grégory Flandin and our partners from Télécom Bretagne, Rabio Labi and Sébastien Houk, which could not make it to the conference. So the advantage of being the fifth and last speaker is that a lot has been explained already about AIS and the context of satellite AIS, so it will save me some presentation time, hopefully. So you don't want to hear that again. Benefits of satellite AIS, so as it has been stated already before, satellite-based AIS will provide traffic monitoring with a global coverage and frequent revisit time. And it will also help to potentially detect and counter illegal activities. For instance, imagine that some vessel is taking some awkward route, or that all of a sudden a vessel stops emitting AIS and close to the Horn of Africa, for instance, could be due to a piracy attack. So a lot of benefits for the sake of maritime surveillance. Also, I want to mention the SAT-AIS program is a joint ESA and AMSA initiative to provide Europe with a future system. And the provision of AIS data will go towards EU institutional organization, but also other bodies. And okay, there is a technical challenge. You heard about it already. Just a few words about the SAT-AIS system so that we share the same understanding and vision. It is composed of a constellation of LEO satellites that will do the job in terms of capture and detection of AIS messages, the worldwide coverage, of course, and the frequent revisit thanks to the constellation. We have the associated ground segment, part of the same system, with the receiving ground station, the mission operations center, satellite control center, data processing center and user segment. And on top of that, we have a concept of operation that is meant to support the maritime surveillance scenario and services for the end users. Performance requirements, it was already very well put in Emiliano's presentation, so I won't spend a lot of time on that, but we have two particularly important metrics. One is a timeliness. It's the latency from the transmission of an AIS message to its archiving in the end user database. So of course it applies to messages that are successfully demodulated. And the time update interval is the time elapsed also for the end user in the archiving database between two consecutive messages coming from the same vessel. Now, we know about the performance metrics, but just a few words about the performance drivers. The timeliness is of course driven by the constellation design and the ground infrastructure, so I won't comment on that, it's out of the scope of this presentation. The time update interval, it captures both the constellation sizing and revisit capability and the AIS payload detection performance, the standalone AIS payload detection performance. And at first glance, it was also in Rémi and Thibault's presentation, but it seems that this metric offers a trade-off between a very large constellation with simple satellites, which would have a low detection performance, versus a small-sized constellation of high-performance satellites. However, it's not that simple, and we will see that in the coming slide. You have to afford a high-performance payload, otherwise your system could be blind. So the AIS payload detection capability, it remains really an essential and critical driver for the mission. What I mean with AIS payload, it's a combination of a lot of stuff, but we have an antenna subsystem, receiver front-end, and processing back-end. Okay, so we can grab the complexity of the SAT-AIS system. We know that the maritime AIS scene is also complex because it's, you need a traffic model, you need to know how the SOTDMA random access works. So we have a complex system, we have a complex reality for AIS, and we need some advanced performance metrics. So end-to-end simulation is really mandatory and essential to make sure that an affordable system exists that can meet the end-user performance requirements. Talking about the models, for the AIS context, you have the traffic model. You need a model that has some accuracy with respect to the traffic densities, that gives also an indication on what are the average reporting rates for the vessels, and also that has the capability to extrapolate in future years, because the SAT-AIS system is supposed to live a long time, up to 2030. So we need some extrapolation capability, which can be a very challenging problem. Of course, you need the access model as well. And for the propagation, you need an emitter model, which covers the antenna modeling, the transmitter characteristics, the vessel trajectory, attitude, etc. Can be part of it. The RF channel model with a lot of propagation models. The link budget takes into account, of course, the antenna pointings, propagation path, some specific attenuation models for this frequency range, and so on. And the satellite system has to be part of the simulator, of course. So it's a bit of a shame because I have the very nice looking video here, but it's not working. But I promise it is even better looking than the one we saw in the first presentation. I'm just joking, but if you want to see it offline, you can come to my PC and it works. Okay. So next, once we have a hand-to-hand simulator, we can grab really the difficulty and the problematic of satellite AIS. It's been explained already, but again, the SOTDMA, the self-organization of the SOTDMA, it works at a local scale, and it will not help you from a satellite viewpoint. It makes even the situation worse. So this protocol works on what we call usually a SOTDMA cell, and don't believe the picture you see here. You don't have 4 such cells underneath your satellite. You can have up to 4,000 cells like this. And then if you take into account, depending on the geographical area, the maritime traffic density and the average reporting rates, you can expect a lot of collisions, co-channel interferences. We have 2 types of such interferences. Obviously, the messages that are transmitted in the same slot. SOTDMA is a kind of slotted LOR with a slot reservation process, to simplify. So it's slotted. So messages transmitted in the same slot index will necessarily collide, but you can also have collision coming from adjacent slots due to the variable path delay from the nadir to the bore site. So this is a kind of intermediate output we can have with an end-to-end simulator. Typically, what I show on the left side is a simplified display of Earth with a view in red of the satellite track during 5 minutes. It's a LEO satellite at 750 kilometers altitude. And we show with the black dots what is the traffic which is visible by the satellite for the duration. And on the right side, I'm showing something which is, in fact, the distribution of interferences or number of interferences for the duration of the satellite path. So this is the average number of interference you will experience. This is the distribution of the number of interference you will experience from the satellite standpoint. So Pacific, it's not a problem. Since you have half empty slots, half slots with a single message, a simple receiver can do the job. Simple receiver being simple antenna and classical receiver algorithm. Now, if we move to Atlantic, we have this time on average maybe 7 or 8 collisions, but it's on average. And in fact, this distribution, it's very close to a Poisson law. It's not exactly a Poisson law because the satellite advances and the average number of vessels underneath the satellite changes. So it's a mixture of Poisson laws where the lambda parameters depend on the average number of messages transmitted. And in fact, it's not even a Poisson law because the SOTDMA protocol, it's not completely random access. So at a local scale, it will somehow create less empty slots because collisions are not possible. So in the end, the distribution you have is narrower than the Poisson law, which is a problem for us because we are really interested in this tail, the extreme hands of the distribution, which is really where, when we have few collisions, we can make the performance expected. Again, here, if you have a simple receiver, it can do the job. You will maybe see all single slot or slots with single messages that will be detected correctly. And it can be sufficient to do your performance because you don't know 100% detection here. Let's be clear about that. It can be enough that for part of the time you detect only 10% of the messages because you have several opportunities per vessel due to the reporting rate, which is between 2 and 10 seconds for a moving vessel. So you have, for a satellite path of 10 to 15 minutes, a lot of opportunities, and you need to detect a vessel only once. So it can work out here. No more problems? Gulf of Mexico, classified as high traffic zone. East Asia seas. Number of interferences moves up to 15, 16 on average. Mediterranean, even more interferences. We can see we have two modes in the distribution. Huh? First, you see the Mediterranean Sea when you are on top of Africa and you have much less collision, and then you start to see Central Europe, North Sea, and so on, and their distribution moves to the left. And Black Sea, even worse. So here is just a summary of this distribution for the number of messages, simultaneous messages you collect from the satellite. Okay, now that we can look at it, just what do we expect from a low performance payload and what do we expect from a high performance payload? A low performance payload would be a simple antenna with a simple algorithm, and the detection would work like this. So on the x-axis, you have the number of interferences experienced at the input of the receiver, and on the y-axis, you have the number of detections. So if you cannot cross the line in violet, of course. And well, with a simple payload, when you have one message, usually you get it, and then from 2 and 3 on, it decreases very fast. You expect from a high-performance payload to have some percentage of detection, maybe above 50%, up to 5 and maybe 10 interferences. And if this happens for a high-performance payload, so high-performance payload will be a complex antenna system with a multi-channel receiver and with quite advanced, sophisticated processing algorithms. So this is the same thing, but in terms of percentage of messages detected over the message received. And okay, if we cross now this with the distributions we had earlier, we can easily understand here that the low-performance payload will be totally blind in any high traffic zones. And we can say, for instance, the high traffic zones start after 7 or 8, for instance, interferences on average. So you can even see, really, for Central Europe, if you consider the Black Sea and the Mediterranean, the minimum number of collisions you will experience, even when you approach the zone, etc., will never be less than 6 or 7. So if you have a low-performance payload, you are totally blind in these areas. Okay. So now going back to the problem of having so many interferences. The received signals are not equal in every aspect, hopefully, and we have a number of sources of diversity. We have diversity in the direction of arrival because from the satellite perspective, not all messages come from the same direction. The incident wave polarization also varies depending on the location of the emitter, and as you may know, the Faraday effect is quite significant for this frequency range. And the IS emitters usually radiate linear vertical polarization, but by crossing through the ionosphere, when the waves incomes at the receiver input, the rotation of the polarization is possibly different for every emitter, and it's a source of diversity as well. So signal strength also depends on many factors, but antenna pointing, propagation path, sea conditions maybe. So we can expect some diversity here as well. Path delay is quite obvious, and Doppler also is significant, plus or minus 4 kilohertz for a satellite at 750 kilometers, which is significant also considering the baud rate of 9.6 kilohertz for AIS. So it can help really to separate messages. Here I have another video. Too bad it's not working. Yes, I wanted just to illustrate the previous slide and show on the upper part, again, a maps display, and on the lower part, a time representation of a sort of chronogram of the collected AIS signals, where, for instance, we have per time slot a bar per each signal, and the height of the bar is related to the amplitude of the message. The bars are time shifted due to the different propagation delays and so on. And you could see on the map what were the emitting vessels, where they are located, and also you had a display of the polarization of each vessel. So it can help to visualize, if you want to take advantage of these sources of diversity, what you can do, what you can expect in a real simulation, and how you can sort messages out thanks to these sources of diversity. This video, again, if you want to come after the presentation, I can show it to you. Now, coming finally to our solution and to the adaptive multi-antenna receiver. We have a receiver front end that is composed of an antenna array. I will give some more guidelines or details in the next slides. A receiver front end with multiple channels. And then we have what I call a processing backend, where we will have a scheme to perform adaptive beamforming. So we will use the antenna array to take advantage of direction of arrival and polarization diversity in the incoming signals. It will work in 3 steps. We'll have to analyze the signals, estimate some parameters regarding the sources, so the number of colliding messages, critical parameters like the DOA and polarization. And once the parameters have been estimated, there are many algorithms to design optimal antenna weights. The latter part of the processing chain I will not comment, but we rely for this solution on a high-performance demodulation scheme, including SIC. And this part of the algorithm will take advantage of Doppler and signal strength diversity. So the SIC is really here to take advantage of signal strength diversity. And the Doppler, I will not comment more than that, but I have put the reference here, and you have 2 of the knowledgeable co-authors sitting in the first row, so if you want more details, you should reach them. Okay, just a little bit of formulas, but I promise not too much. For the antenna array, so we propose a uniform linear array, but we can have a uniform planar array as well. And we propose per each position in the array geometry to have a dual polarization antenna. So that will be capable of radiating a field with 2 orthogonal polarizations, preferably 2 linear orthogonal polarization, could be circular orthogonal polarizations. So we have 2 times p element. 2 is because of the dual polarization. And we assume here we have k impinging sources, signals, key simultaneous signals received by the sensor array. And then we know from literature that we have a linear relationship, it's a simplified model, between the vector of sources and the vector of sensors. And the antenna weights, if you look at the antenna weight that links one source signal to one sensor signal, it carries information. The phase shift carries information on the direction of arrival of the signal, whereas the amplitude carries information about the polarization of the signal. The amplitude, of this coefficient carries information about the polarization. It's the polarization loss factor, in fact. Okay. So a classical way to proceed is really to compute the array covariance matrix. And a well-known result is that the k first eigenvectors, or maybe better put, the eigenvectors that are the k first strongest eigenvalues, they span the same subspace as the column vectors of matrix A that we saw earlier, which we call the signal subspace. And so first, if we want to estimate the number of sources, there are some well-known results in the literature. I have put a reference here. We have some criteria coming from information theory that just look at values of the eigenvalues, or respective value of the eigenvalues. And based on that, you have several estimates possible to find the number of sources. Usually, if the number of sources is less than the number of sensors, and if the signal-to-noise ratio for each source is good, it works very well. Now about parameter estimation, we have to estimate the direction of arrival and the polarization. So we rely on derivative of the Esprit technique. For the DOA estimation, we split our array into 2 subarrays, where we take for the first subarray to the last but one element, and for the second array to the second to the last element. I don't know if it's clear. And then we can expect also a linear relationship between these 2 subspaces, and the eigenvalues of the multiplication matrix between these 2 subspaces carries information about the direction of arrival. So that's one estimator. For the polarization estimation, we split the arrays in a different way. We have the array with all horizontal polarization and the array with all vertical polarization. And again, if you look at the 2 signal subspaces for the 2 subarrays, you have a linear relationship where the multiplication matrix carries information about the polarization. So here we have a simplified model because we have only linear polarization on the emitting side and receiving side. So we have only one parameter, which is orientation of the polarization vector, and the ellipticity is null, so we have only one parameter to estimate. Again, this is well known in the literature, and you have references in the article. For the adaptive beamformer, now that we know from where and with which polarization all signals income, the objective is to maximize the signal to noise and interference ratio and to design specific weights for that. And the idea is that we want to steer the beam in the direction of one of the source, which is the source of interest, and we want to match its polarization to have the maximum gain. And while we do that, we would like to use a complete antenna array and the complete set of weighting coefficients to minimize the gain for the other interferences, and it can be done by simply cancelling the polarization or by having a destructive combination geometrically with a phase shift, so by doing some beam nulling. So there is a well-known method which was proposed by Capon, which in fact sees that as a minimization problem. So if you consider the output power of your sensor array that has been weighted by a set of complex weights, you want to minimize the output power by maintaining a unitary gain in the direction of the source of interest and for the polarization of the source of interest. And you have a well-known solution for this minimization problem, which is put there. Okay, now let's look at an example. Maybe it will be better. So here I'm considering an array, which is a very simplified display here with blue crosses, 2 times 5 elements, and 4 interferences. So we have less interferences than array elements, so we can expect to find a solution, a good solution for that. Nevertheless, you can see that all the sources are almost in the same region. So here you can see the direction of arrival, because it's where you have the red dot on this map display. And this is the line that crosses the dot is a polarization orientation for this incoming signal. Okay, so we have normally in spherical coordinates 2 angles to designate the direction of arrival, but because we propose here a one-dimensional array, what we do is we can only estimate, of course, the angle projected in the dimension of the array, which is what is put in the formula below here. So these are the angles that we should estimate. Okay, so now what happens if we perform the source parameter estimation? For the number of sources, I'm showing the result with the 2 criteria that we proposed earlier. And you can see that indeed these 2 curves reach a minimum at 4, which is exactly the number of interferences we have. So this part is easy. For the DOA polarization, I have put here in a specific representation. On the x-axis, I have the direction of arrival between minus 90 to 90 degrees, but based on the altitude of the satellite, it should more income between minus 65 to 65. But it's one-dimensional again because it's projected in the direction of the array. And on the y-axis, we have the polarization angle, which is naturally between the orientation of the polarization vector between minus 90 degrees to 90 degrees. So here I have positioned with red dots the original sources and with blue boxes estimated sources, and we see we are quite correct, except for the polarization, where we have an error of around maybe 10 degrees for one of the sources. So once these parameters are known, we perform for each of the 4 sources we have estimated adaptive beamforming, and we will design this kind of patterns. I'm sorry, it's not very nice looking on the beamer. But the first pattern, basically, we focus on the green. The green dot, the green square is always the source of interest, and the magenta diamond are the interferers. And you see that with the antenna weights that we estimated with the Capon method, we have some kind of optimality because we cancel the gain is near 0, close to the interferers, and we maintain a gain of 1 on the source of interest. So it works more or less for the 4 signals we try to estimate. And from these patterns, we simply estimate the signal to noise and interference ratio to show that we are in a good spot to succeed with the demodulation because we are above 10 dBs for everyone. So it should work out. Now, what is the alternative that we will benchmark to in the coming slides? It's what we call the conventional beamforming, where in fact you have to decide for a number of beams and you will steer in regularly spaced fixed directions, and you will synthesize polarization also with a regularly spaced polarization angle. So here we show only for the two polarization. Again, always in the same space, polarization on the y-axis, direction of eyeball in the x-axis. So if you take a X-cut, you see the well-known array pattern with side lobes and array lobes. And on the y-axis, you see you have cancellation. So you have the kind of log of a cosinus square where you cancel the polarization. So here we do already 2 times 5 beams, so total of 10 beams, which is already more than the 4 beams we had earlier. So it's more complexity because every time you do a specific weighting, you have to call your demodulator afterwards. And there you see that none of these patterns really suits well to this situation where the sources are so close together. Such that, in fact, if you take out of these 10 patterns the best signal to noise and interference ratio that you can get, for most of the sources, it's below 0. So demodulation is probably not possible. And for .8 dB, maybe it's 50-50, depends on your receiver algorithm. Okay, so now just last 3 slides showing some results. We have put a simulation benchmark. This time we have used 10 pairs of cross dipoles spaced by half wavelengths. And we have benchmarking the conventional beamforming algorithm that I just explained. And we use M directions and N synthesized polarization, so a total of M times N beams. And for M and N, we have used 2 values, P divided by 2 and 2, which yields about the same number of beams as the adaptive method. So it's a kind of fair comparison because most of the computational complexity is on the demodulation scheme, not really on the adaptive beamforming step. And then, okay, let's say now we afford to put some more complexity into the conventional approach, and we go to 4 times more beams. So we have P direction times 4 polarization. So we do horizontal, vertical, and the 2 diagonals. And we compare that to the proposed solution, which is Esprit Capon for parameter estimation, Esprit for parameter estimation, and Capon for the beamforming part, the weight estimation. So now, how are we going to benchmark this algorithm? So in the scope of this article, we do not perform a complete full-blown end-to-end simulation. We just propose to use representative simulation contexts that come from the end-to-end simulator. And this simulation context, we just sort them by number of interferences. But they are real contexts. I mean, they correspond to a traffic representation, a position of the satellite, link budgets have been estimated, Doppler have been calculated. They are not randomly, I mean, signal parameters are not randomly chosen here. It's real simulation somehow. And then per each number of interference, we have 5,000 cases, and we average the number of detections that is achieved by these methods. We average it for each case of number of interferences. So this is what we get in red, the proposed solution, which scales up until the number of interferences becomes equal to the number of array elements minus 1, which is obviously the limit of the methods because the estimation requires a full determined problem. So when the problem becomes underdetermined, the estimation starts to fail and the performance drops. Yet you can see that with the conventional beamforming, even if you use the same number of beams or 4 times more beams, you are still below the performance of this adaptive beamformer. Okay, so we could go backward a couple of slides, but if you recall the curve we had for the high performance payload, we expected between 5 and 10 interferences to detect at least 50% of the messages, and this is what can be achieved here with this solution. Okay, as a conclusion, so we have a proposed solution which combines the dual polarized antenna array with an adaptive antenna weighting procedure and a high performance demodulation scheme. And we believe it is one of the suitable candidates for high performance satellite AIS, as it outperforms the conventional beamforming approach. So it tends to say you should go for adaptive and not fixed beamforming. And in terms of perspective, I think as we saw, the performance, maybe, of course, it has to drop when the number of sources is more than the number of elements, but we could still improve in this area and look into other estimation routines, knowing that Esprit really requires that you have less sources than array elements. So thank you for your attention. This concludes my talk, and I would like to express acknowledgements to ESA Tech for making this work possible. It was performed under ESA contract for the Phase B1 study. SATIAS. Thank you.
Question.
Maritime surveillance scenario and services for the end users. Performance requirements, it was already very well put in Emiliano's presentation, so I won't spend a lot of time on that, but we have two particularly important metrics. One is the timeliness. It's the latency from the transmission of an AIS message to its archiving in the end user database. So of course it applies to messages that are successfully demodulated. And the time update interval is the time elapsed also for the end user in the archiving database between two consecutive messages coming from the same vessel. Now, we know about the performance metrics, but just a few words about the performance drivers. The timeliness is, of course, driven by the constellation design and the ground infrastructure, so I won't comment on that. It's out of the scope of this presentation. The time update interval, it captures both the constellation sizing and revisit capability. Yes, thank you for the introduction. And so, as you stated, this paper on the adaptive multi-antenna receiver has been co-authored by my colleague Grégory Flandin and our partners from Télécom Bretagne, Rabio Labi and Sébastien Houk, which could not make it to the conference. So, the advantage of being the fifth and last speaker is that a lot has been explained already about AIS and the context of satellite AIS, so it will save me some presentation time, hopefully. So you don't want to hear that again. Benefits of satellite AIS, so as it has been stated already before, satellite-based AIS will provide traffic monitoring with a global coverage and frequent revisit time. And it will also help to potentially detect and counter illegal activities. For instance, imagine that some vessel is taking some awkward route, or that all of a sudden a vessel stops emitting AIS and close to the Horn of Africa, for instance, could be due to piracy. And the AIS payload detection performance, the standalone AIS payload detection performance. And at first glance, it was also in Rémi and Thibault's presentation, but it seems that this metric offers a trade-off between a very large constellation with simple satellites, which would have a low detection performance, versus a small-sized constellation of high-performance satellites. However, it's not that simple, and we will see that in the coming slide. You have to afford a high-performance payload, otherwise your system could be blind. So the AIS payload detection capability, it remains really an essential and critical driver for the mission. What I mean with AIS payload, it's a combination of a lot of stuff, but we have an antenna subsystem, receiver front-end, and processing back-end. Okay, so we can grab the complexity of the SAT-AIS system. We know that the maritime AIS scene is also complex because it's, you need a traffic model, you need to know how the SOTDMA random access works, so attack. So a lot of benefits for the sake of maritime surveillance. Also, I want to mention the SAT-AIS program is a joint ESA and AMSA initiative to provide Europe with a future system. And the provision of AIS data will go towards EU institutional organization, but also other bodies. And okay, there is a technical challenge. You heard about it already. Just a few words about the SAT-AIS system so that we share the same understanding and vision. It is composed of a constellation of LEO satellites that will do the job in terms of capture and detection of AIS messages, the worldwide coverage, of course, and the frequent revisit thanks to the constellation. We have the associated ground segment, part of the same system, with the receiving ground station, the mission operations center, satellite control center, data processing center and user segment. And on top of that, we have a concept of operation that is meant to support the maritime. We have a complex system, we have a complex reality for AIS, and we need some advanced performance metrics. So end-to-end simulation is really mandatory and essential to make sure that an affordable system exists that can meet the end-user performance requirements. Talking about the models, for the AIS context, you have the traffic model. You need a model that has some accuracy with respect to the traffic densities, that gives also an indication on what are the average reporting rates for the vessels. And also that has the capability to extrapolate in future years, because the satellite system is supposed to live a long time, up to 2030. So we need some extrapolation capability, which can be a very challenging problem. Of course, you need the access model as well. And for the propagation, you need an emitter model, which covers the antenna modeling, the transmitter characteristics, the vessel trajectory, attitude, etc. Can be part of it. The RF channel model with a lot of